Hello everyone, my name is Anvo Doan from the Technical University of Munich. I would like to present you, on behalf of my colleagues and industry partners from ARI and SmartRay, the results of our research entitled Parameter Optimization of Approximate Image Processing Algorithms in FPGAs. In the context of image processing, the need for computational power has significantly increased over the past few years due to the demand regarding high resolution and frame rate. In a video camera, the rendering of an image is obtained through the processing of the light captured by the image sensors with several specific image processing operations. For high-end professional cameras, this processing is often achieved with dedicated hardware such as FPGAs that can contain complex architecture and millions of logic elements. Usually, the implementation on hardware is characterized by the resource utilization, such as power, performance, and area or cost. For the image quality, the accuracy is often measured with metrics defined from the human visual perception or with signal-based metrics. When applying approximate computing, a new parameter called necessary quality is introduced and is used to trade off result accuracy for hardware resources. Approximate computing involves several design challenges. First, there are many approximation techniques for different target levels such as device, circuit, memory, algorithm, architecture, etc. For each of these techniques, several approximation parameters need to be defined in order to achieve the best trade-off regarding accuracy and resources. Additionally, it is often beneficial to combine different approaches to achieve better results, and all these configuration possibilities lead to a large solution space to explore. To measure the quality of the results, we often need to define metrics that depend on the target application. Besides, when combining different approximation techniques, error can propagate and interact, which is also a key challenge that needs to be considered in an optimization process. Finally, finding interesting trade-off in a large design space is also a tedious task, requiring methodologies to efficiently perform design space exploration. In this work, the target application is an image color processing pipeline which consists of 3 steps. The first step of the pipeline is tone mapping, which maps the input image luminance to the display luminance. This is a nonlinear function that can be implemented in a lookup table. In the second step, called color space conversion, input colors are transformed to match the target color space. This operation is carried out by a matrix multiplication of an RGB triplet with a 3x3 matrix of constants. The last step is EOTF compensation, which is used to adapt the input image to the characteristics of the display. Similarly to the tone mapping, this operation is performed with a nonlinear function that can be implemented as a lookup table. Now that the target application has been presented, let us have a look at the approximation parameters that need to be explored. Since tone mapping and EOTF compensation are nonlinear functions that can be implemented as lookup tables, we can approximate them using sparse tables. The approximation concept of these sparse lookup tables is illustrated on the bottom left figure. The nonlinear function is divided into uniform sections, and each of these sections can be further divided into uniform subsegments. The table on the right summarizes the different parameters which consist of the interpolation type, the number of uniform sections, and the number of subsegments. Let us note that the number of subsegments depend on the number of sections, which is a constraint that needs to be considered when defining the optimization process for the design space exploration. For the color space conversion, a matrix multiplication is applied. This is illustrated in the bottom left figure for the conversion of a single channel. For this operation, the considered approximation parameters are summarized on the table on the right. These consist of the number of fractional bits of the matrix entries, the number of fractional bits of the intermediate results, the type of approximate adder, and the parameters depending on the adder type. For the objectives we want to optimize, we need to consider the hardware utilization such as area and power, and the image quality. The area is computed as the sum of the utilized DSPs, BRAMs, LUTs, and registers for which the values can be found in libraries. The power is then derived from the area using tools such as the Intel Early Power Estimator. For the image quality, we choose to use the delta E value defined as a perceptually uniform color difference measured by the International Commission on Illumination and is easy to interpret for image color specialists. So we have a processing pipeline which combines different approximation techniques, each of them having their own approximation parameters. This leads to a huge solution space in the order of magnitude of 10 to the power of 280. For the objectives, we want to simultaneously minimize the power, the area, the maximum delta E value, and the mean delta E value. Given the multiple objectives and the large solution space, a common approach is to use a meta-heuristic for the design space exploration. In this work, we use a well-known multi-objective genetic algorithm called NSGA2 and propose a suitable optimization model for the approximation pipeline we have presented. In the optimization model we propose, an individual is represented with an explicit encoding for the approximation parameters defined previously. These parameters are simply concatenated into a list, allowing to take into account error propagation and interaction. Also, that allows a simple definition of the crossover and mutation operations. The genetic operations are defined for each pipeline step separately and ensure that feasible solutions are always produced. The tone mapping and EOTF compensation steps have the same crossover operation, which ensure that the constraint between the number of sections and the subsegments in the sparse lookup table is satisfied with techniques called upsampling and downsampling of values. The crossover for the color space conversion takes into consideration the RGB color channels in order to distinguish them. For the mutation, we either randomly regenerate the values for a pipeline step or for a part of a pipeline step. Now coming to the experimental setup. When assessing the quality of a color processing pipeline, exact values can only be given when all possible colors are tested. For a bit depth of 16 bits per channel, that means 2 to the power of 48 colors, which would make the evaluation prohibitively long. Instead, we use as input a subset of the input space by sampling the color space in 64 steps for each channel, creating a dataset of 64 to the power of 3 colors evenly spread across the color space. Additionally, to minimize potential effects related to the perfectly even sampling, we add random noise to every data point. So, we have as training input a single image that is illustrated here. The validation of the optimized approximation parameters is carried out on a reference set of real 16-bit images defined in the literature. Regarding the results, first, let's have a look at the convergence of the algorithm. Here we depict the evolution of the hypervolume indicator, which is a widely used metric in the literature for analyzing convergence and diversity. We observe that the algorithm converges fairly quickly, achieving good values below 1,000 iterations. Now let's have a look at the Pareto front we can obtain. Here we have a projection showing the maximum delta E value as a function of the power. We observe an L-shaped Pareto front, meaning that in the horizontal part of the L, a small sacrifice on quality can lead to a substantial decrease of power consumption, whereas in the vertical part, even a large concession on quality only brings a small decrease of consumed power. Furthermore, the Pareto front has good diversity, showing values of delta E ranging from 0 to 182 and demonstrating that the proposed model is able to implicitly consider the interactions between the different approximation techniques used in the processing pipeline and their related error propagation. To illustrate the potential trade-off analysis that are possible, we will consider an image application where quality can only be sacrificed up to a point where it remains as invisible as possible to the human eyes. Usually, it is considered that a delta E below 2 means that color differences can only be perceived through close observation, and delta E below 1 means that they are imperceptible. Therefore, the region of interest lies in the knee of the Pareto front, which has been zoomed in. From that region, we have sampled 5 different solutions for the validation. Here is a table compiling the evaluation for these 5 points. Compared to the reference design without any approximation, we can observe that the worst selected point in terms of power still consumes close to 89% less while achieving a low max delta E of 0.1 for the training image and the test set. Regarding the image color quality, despite the training set only consisting of a synthetic image, the values of max delta E and min delta E for the test images are fairly similar. This means that trade-off analysis can be made with evaluations obtained from a training consisting of a single synthetic image, and designers can therefore easily define their trade-off focus depending on the delta E value they want to achieve. Coming to the conclusion, in this work we have proposed an NSGA2-based optimization model for an approximate image color processing pipeline, which can inherently consider interactions between approximation techniques and error propagation. The algorithm shows good convergence and good results even with a training set consisting of a single synthetic image. The obtained results allow easy quantitative trade-off analysis and are easily interpretable for experts in the field. As future work, we want to explore more complex applications and refine the proposed model. This concludes the presentation, and if you have any questions, feel free to send us an email to the address shown in the first slide.